Hello everyone. So in this video, we are going to solve one example problem, and this is an example on critical clearing angle and critical clearing time for a power system. So this is a continuation video. There's a another video where I've explained the theory, and in this video I'm solving the problem. So please, if you don't understand this, refer to the theory in the another video, and then you can continue with this. So the question is like this: there is a generator whose internal EMF generated is E at an angle of delta. So right now we don't know what is the value of E and delta. The direct axis reactance of the machine is zero point 0.2, and then H of the machine is 5 seconds and F is 50 hertz. And then the reactance is 0.1. This is the step-up transformer where it is there, and then there is a transmission line whose reactance is 0.25. So of course these all reactants are all imaginary, so should be mentioned J. Now what I have next is to find out what is the critical clearing. So assuming that there is a fault, what is the critical clearing angle and critical clearing time, and then this PE is the power that is being injected into the infinite bus, that is 1.0 at angle 0 at 0.8 power factor lagging. So power factor is also given at which the power is being injected. So let's get started by solving this problem. So first thing I would like to do is to find the current. So this is the current I. How much current is being injected into the bus? So I know this. So what is the complex power? So we know that active power by complex power is nothing but power factor. So this is zero point 0.8. It is given to us, and here it is 0.6 by S. So from this I can find what is the S. So this implies S is zero point 0.6 by 0.8, which will be, so let me use my calculator for this. So 0.6 divided by 0.8, 0.75. So 0.75 per unit is the complex power. Now what is the reactive power Q? So Q will be S square minus P square under root. So there are other ways to find it. I'll just use that. So square root of 0.75 square minus 0.6 square will give me the reactive power, that is 0.45. So 0.45. So finally I can represent, this is the magnitude of S. So I can represent S as a complex number, that is P minus JQ. I am using minus sign because it is given as a lagging power factor. So therefore active power is 0.6 and reactive power is 0.45. So this is my S, the complex power supplied to the infinite bus. Now what is I? So we know that I is nothing but S conjugate by V conjugate. So S conjugate, I'll take 0.6. Now I take it as plus, and then the voltage V is just 1 angle 0 degrees or minus 0 degrees for V conjugate. So that will be same. So finally I'll get the current to be 0.6 plus J 0.45 per unit. This is the current in the line. So first step we have done, that is calculation of current in the transmission line. And once I have the current in the transmission line, I can actually add all the voltage drops. So here 0.2 is the impedance, 0.1 is the impedance, and 0.25 is the impedance. So total impedance or total reactance of the line is 0.2 for the machine and 0.1 for the transformer and 0.25 for the line. So this is all with J. So this is J 0.55 per unit. So from this I can find total voltage drop. So voltage drop is nothing but I into X total. So that is nothing but this I into X. So, and if I add this voltage drop, then I'll get the E. So E as a vector will be nothing but V plus the drop, that is I into x total. So let's calculate that. So I go back to my programming environment. So I'm just writing the simple code on the left here. So I is 0.6 plus 0.45 into I, and then x total. So x total equal to 0.55 into I. So this I is square root of minus 1 as defined as a constant in Octave or MATLAB. So from this I'll get the, so my voltage is 1.0 at angle 0, so I'm not defining that. So E will be the internal EMF of the machine. So that will be V plus I into X total. I'm sorry, it looks like I made a mistake. So this should be plus and this should be plus, whereas here it should be minus. So here it will be minus, and finally in my code also it will be minus. So current should be lagging. That is how I found out. If the current is leading, then the power factor will be positive. So anyway, let me execute this. I'll store it. So here I am getting E is 1.2475 plus this. So let me convert E into real and imaginary components. I'm sorry, the E into polar form. So absolute value of E and angle of E. So into 180 by pi. So 1.29 is the E and then angle is 14.81 degrees. So 1.29 at an angle of 14.8 degrees. So this is my internal EMF of the machine. So therefore, my delta naught is 14.8 degrees. So now talking about stability, so my operating point delta naught is 14.8 degrees. So therefore, what will be my delta max? So delta max will be nothing but pi minus 14.8 or 180 degrees minus 14.8 degrees. So delta max will be, so I'll just store this, d naught equal to this, d max equal to 180 minus d naught. So here I can see 165.18 degrees is the delta max. Now once I have this, or 160.2 degrees, so these two should add up to 180 degrees. Now I have these two. So we had in earlier video discussed the expression for critical clearing angle. So this is the critical clearing angle. So from this I can find the critical clearing angle. So let me just have this. Here I also require what is PM and Pmax. So let me write down those quantities also. So PM is the mechanical power input, which will be equal to the electrical power input during the study. So this is PM, that is 0.6. Now what is Pmax? So Pmax is nothing but EV by X. So E we calculated 1.29, I got it. And V is 1 and my total X is 0.55. So this will give me my Pmax. So PM equal to 0.6 and then Pmax equal to 1.24, or I can just use this absolute value of E divided by X total. So absolute value of extrude. So I'm getting P max as 2.3462. So 2.346 per unit. So now that I have all the quantities, I'll directly use this formula to calculate critical clearing angle. So what is the formula? I'll just show that to you. We had derived this formula in another video. So just we'll apply that now to get the values. So I have, so one thing you should know here is that these deltas all should be in radians. Right now, we had for our understanding, I had displayed it in degrees, but I will have to convert this into radians. Let's do that. So PM by P max into delta max minus delta naught. So let me first type that PM into delta max minus delta naught, and this quantity I will just uh, convert into radians, and then this whole thing I'll divide by P max. So this part of this term I completed. So plus cos of delta max, so plus cos of d max. So again this I divide by 180 and multiply by pi. So this whole thing I'll apply cos inverse A cos. So then I'll get delta C, critical clearing angle. So this delta C will be in radians. So just for our intuition, I'll display it in degrees. So into 180 by pi. So let me run this code. So there is error line 14. Okay, so PM star. So I just forgot to give the multiplication symbol. Okay, so let's run it. So here I am getting 107 degrees, or delta C is 1.87 radians or 107 degrees. So let me write down in my diagram. So as long as I am going up to, this is 107 degrees. So up to 107 degrees, before that if I clear the fault, then the machine will be in stability, otherwise it will not be in stability. So from formula, so let me copy that formula here, or from formula of delta C. So I get delta C equal to 107.19 or 2 degrees. Now what is critical clearing time TC? So even critical clearing time TC, we had derived a formula in the previous lecture. So this is the one. So 4h into delta C minus delta naught by omega PM. So let's do this. So TC, critical clearing time, is square root of, in the numerator I have 4h, so 4 into h. So h is given to be 5 in the question. So multiplied by delta C minus delta naught. So delta C minus delta naught. Remember delta C is anyway in degrees. So delta naught is in, sorry, delta C is in radians, delta naught in degrees. So I am just converting that. Then I divide this by, again bracket open, omega, that is 2 into pi into, frequency is given to be 60 hertz for this or 50 hertz for this problem. Omega is 2 pi f, and then PM is 0.6. So finally this will be my value for critical clearing time TC. So let's run this. So I'm getting 0.4136 seconds. So 0.4136 seconds or 413 milliseconds. or 417 milliseconds. So finally, the fault has to be cleared before 417 milliseconds so that the stability is maintained. So if the fault is not cleared within 417 milliseconds, then the machine will lose synchronism. So, so looking at the diagram once again, just to get the feel, there's a generator generating power and then injecting power and into the infinite bus. There is a fault which is occurring here, and this fault has to be cleared within 417 milliseconds. Otherwise, the generator will lose synchronism with the grid. So that is what is the importance of critical clearing angle and critical clearing time. In this video, I had shown the numerical example. In the previous video, I have shown the derivation. So you can view both together. Thank you.